Today we want to look more at flux integrals. Remember what we're thinking of. We're imagining a vector field flowing through a surface. One of the things that we need for it to happen here, since the dot product can be positive or negative, it's always going to be a scalar, but it'll be positive or negative or zero, is the surface needs to have an orientation. We need to assign a direction to the surface. Just like when we were calculating line integrals, we needed an orientation to the curve. The curve needed to have some kind of direction. Since we're describing the surface with a normal vector, and since a surface will have two normal vectors, a right-handed normal vector and a left-handed normal vector, it's going to be important for us to decide, and since they're just going to be -1 times the other, it's important for us to indicate what the positive orientation is. So that's what I've done with each of my regions here. I've oriented this region generally going up, and this region going what we would call up from the surface, unless we're looking at it from down below. I don't think anybody's watching this from Australia, so we're good. So we can have right-handed orientation, or we can have left-handed orientation. See the whole thing, the angle. So we just need to pick one of the directions to be positive. Just like on a curve, we had to pick one of the directions to be positive, from P to Q or from Q to P. So normal vector is right-handed, normal vector is left-handed. So the questions that I want for this, I've just defined a vector. I want to calculate the flux of this particular vector, 1i plus 2j minus 3k through two different regions. The first region is this square parallel to the xy plane with an area of 4 and nice, simple to find corners. And then our second region is a rectangle, but this rectangle is at an angle. So I have the 3/4 view, and I've got the side view here. Side view is pretty effective since we're not doing anything with y. So the first question is, we want to look at this particular problem that we set up. Why do we not need integration in these calculations? We're not going to need integration in these calculations. I want to know why. I want you to think about whether the flux is going to be positive or zero or negative. And then I want you to calculate the flux. So pause the video here and think about these questions. All right, welcome back. Let's look at these problems, this vector flowing through these two regions, region 1 and region 2, cleverly typed. So the first thing I wanted you to think about was why we don't need integration on these problems. I mean, this is calculus class. Shouldn't everything be integration? Now, we need to understand integration. We need to understand when not integration as well. We have to learn things backwards and forwards. The reason that we don't need integration is two. There's two reasons. Number one, the vector is constant. The vector is constant. And so we don't, that's not continuously variable. Continuously variable factors, that's what triggers integration. So first factor, our vector, which is the vector field part, constant. Number two, notice that this normal vector A is the normal vector everywhere in the region. I can describe this entire region with just the one vector. So we don't need integration because the vector field and the surface are constant. So we don't need integration because the vector field and the surface that could be misinterpreted by saying that the surface is constant. The vector field is definitely constant. It's just one vector everywhere. But what I mean when I say the surface is constant is that we can describe the surface, we can describe the region with just one vector. Take the area, multiply by a normal unit vector. The surface, what I mean when I say the surface is constant, is we can describe the surface with one vector. One normal vector. Get Rocketbook to sponsor. I made a mistake. Good thing I can quickly erase that before I scan my notes on my Rocketbook. Oh, it's on. I don't have that. Flip it over this way. In influencer fashion, I should be like, oh, here are some other colors. Rocket is going to have to send me some other color ones. We can describe the surface with one normal vector. The area is 4, but it's the same normal vector at all points. So for region 1, I'm going to describe the area vector with 4k. 4 is the area of the area, and k is a unit vector normal to the surface. So we want the magnitude the area So the parts we want for the area vector, we're going to take the area as the magnitude and a unit normal vector for direction. Area is the magnitude. And a unit normal vector is the direction. The reason we want a unit normal vector for the direction is that we want the area to represent the magnitude. So I want the magnitude of the area times the magnitude of the direction vector. I want the magnitude of the direction vector to be 1, so that all we're getting from the unit normal vector is a direction, and all the magnitude to be summarized in the area. So for region 1, the area vector will be 4k. 4 is the area of the region. K is a unit vector normal to the region. So I'm taking the area and multiplying it by 0i plus 0j plus 1k, which is a normal vector. Sorry, which is a unit vector. So for region 1, we want to speculate whether the flux is going to be positive, 0, or negative. Notice that the orientation of the surface is generally up in the z direction. It's 0 in the x and y, so the orientation is all up in the z direction. The vector coming through this surface is 1 in the x direction, the surface doesn't care about that. 2 in the j direction, the surface doesn't really care about that, but -3 in the z direction. So the vector is coming through at 1, 2, -3. It's going backwards against the orientation of the surface. So from, let's just go from this point. If I go 1, 2, -3, there's the vector v. The important part is the -3k is going the opposite direction of the +4k from the surface. So they're going in opposite directions. So we expect the flux to be negative. The surface is generally up or all up, and the vector is down relative to that surface. So we expect it to be negative. When we actually calculate the flux in through region 1, it's just going to be v dot a. The reason we get away with multiplication and we don't have to integrate is that the vector is constant and we can describe the surface with one normal vector. So the flux is just going to be the vector 1I plus 2j minus 3k dot our area vector, which is 0I, 0j plus 4k. So the 0 times 0 plus times 1 plus 0 times 2 plus 4 times -3. -12. Negative as we expected, 12 because it was 4 from the vector going up, -3 from the, 4 from the area going up, -3 from the vector kind of going down. In the second example, or for region 2, we don't need integration for the same reason. We don't need integration because the vector is still constant, and the surface can be described with one normal vector. The area of the region is 2 square roots of 13 because I made the x 2 instead of 4. I wrote down 2. I'm like, oh, that should be 4. I'm like, oh, I'm just going to use 2. That'll be easier, right? And then the other part of my brain that said it should be 4 is like, oh, all right, go ahead. We could have had a 5 here. This could have been like a 10, but no. But nope. It's fine. We're professionals. We can deal with an area of 2 square roots of 13. But what we need, that's going to be the area of the region. That's going to give us our magnitude. I need a unit vector for the direction. So we need to come up with a unit vector for the direction. Then we'll have our vector that flowing through our surface, which we can describe with one vector. That's what we mean when we say that the surface is constant. It's not continuously variable because we can describe the surface with exactly one normal vector. Mainly because there's one normal vector for one normal unit vector for the whole surface, and we just multiply that by the area. So all we have to do is come up with a normal vector for this surface. Now, if I do that right now, then obviously flux integrals will be solved and we'll ace everything that comes along after this. Even when I start talking about divergence theorem, if I give you this normal vector right now, everything will be perfect and you will understand calculus all the way up and down. You'll even understand things that you didn't understand before for Calc 1 and Calc 2, but only if I come up with this unit vector right now. If I wait any longer, then you're going to have to go through Calc 3 at the normal rate and you'll still have misunderstandings about Calc 1 and Calc 2, and it'll be tragic. But I can plug you into the matrix by telling you what this normal vector is right now. So let me tell you that normal vector is, oh, dang it, look at the time. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.